So I believe that everyone should be pretty familiar with some of these concepts. So we're going to move through these a little bit more quickly, and then if you have any questions, you can actually watch my other YouTube playlists where we kind of go through this a little bit slower, because I'm assuming that a lot of people have some basic material science background. But anyways, material science is basically founded on this idea of this materials tetrahedron. So one of the kind of mantras we'll be hearing over and over and over again is that structure will dictate properties and performance, and we can perform different processes to basically impact or influence or change structure, which thus then changes property and performance all over again. And we are at the center of this tetrahedron. We perform experiments, we do modeling, we characterize materials, so that's what we want to do. So one of the basic kind of concepts is if you melt titanium in an ingot, this big ingot, you can go and send it through rollers. That spits out kind of this flat sheet of metal. And in this sheet of metal, initially you have kind of these large grains when you just melt the material. Once you do this process, which is called cold working, you then make this tiny sheet of metal, and inside that structure now, the grain size is much smaller. So you change the structure, and then you've also created dislocations in this material. So I've decreased my grain size, I've increased my dislocation density, and thus it's going to impact the properties and performance of the material. Specifically, my yield strength will scale as dislocation density to the 1/2, and it will also scale, change in yield strength, as my grain size to the -1 up to 10 nanometers. So by doing this process of cold working, I've changed the structure of my material. It's influenced the property, my yield strength, and thus impacted the performance. Higher yield strength meaning that I can yield basically it takes a larger stress to yield the material, but I usually pay a price in ductility as well. So that's kind of the idea here, and we're going to be returning to this throughout essentially this class, and that basically we're going to be kind of running through this. So we're going to be looking at a lot of different types of materials in this class. So metals, polymers, ceramics, composites will be the one that we focus on the most. These are kind of materials that we may kind of discuss in passing, and we're going to be really focused on, in this class, structure, thermal properties to some point, but mechanical properties. So in this class, we're really going to focus on these. So it's all going to be about materials, how do they mechanically perform, and then how can we predict or look at those. But before you move into kind of mechanical properties, we have to look at, again, how, when you, basically perform or actually impart a stress on a material, what are you doing atomistically? Well, at the most fundamental, at the smallest length scale, you're pulling on bonds. So we have two classes of bonds, intramolecular and intermolecular bonding. Intramolecular bonding comes in three kind of prevalent, large types. And it really depends on basically how the valence electrons are distributed or shared. So intramolecular bonds, you can see here we have covalent, where we share bonds, right? Ionic bonds, where bonds are given up or, taken, or basically either they're given up or they're taken. And then metallic bonding, where our bonds are, or actually our electrons are delocalized. But one key thing you'll notice here in metallic bonding, ionic bonding, and covalent bonding, their bond strength is greater than kT. What does that mean? These bonds are static. They cannot break and reform dynamically at room temperature. So that is one critical kind of thing kind of to think about. And when we think about bonding energy, we kind of have to touch on a little bit of thermodynamics. So remember, we are always trying to lower the free energy of our system. And we have two kind of critical, there's always kind of this energy competition. And we're going to go through this in class quite often. Enthalpic energy contribution and entropic energy contribution. And enthalpic interactions are basically energy that's stored, basically in bonding. So if things like to bond to another, they will have lower energy, negative enthalpy. Usually things are, either really repel against each other, or they have kind of no interactions. You've probably heard of Henry's law, ideal mixing, so there's no real interaction. Entropy is not disorder. Entropy, the one that we're going to kind of talk about the most, configurational entropy, or conformational entropy, configurational or conformational, it's basically the number of ways that I can kind of distribute something. So for example, let's say I have I have some red balls, and then I have some blue ball types. There are different ways that I can distribute and kind of arrange these. So each of those represents a microstate. So a distinct way that I could rearrange those two kind of balls. And the entropy scales, this is Boltzmann, again, cocky fellow who put this on his tombstone, but you deserve it when you have an equation named after you. And entropy will scale increase as those number of microstates increases as well. So we have to kind of pay this kind of competition, this price. So those are going to be kind of the two energy competitions that we're going to kind of deal with a lot. And here's some additional information if you want. And this, all of these notes are available on the UOP OER website for free. So you can do first law of thermodynamics, second law of thermodynamics. Again, we must increase the entropy in our universe. It can never be negative. And different types of work that can also be done on our system as well. Why do I mention this? We want to go way back into kind of this idea of bonding and potentials. And next time, we're going to get into this because this is going to be a very, very, very critical part. A very, very critical part. We're going to come back to potentials a lot in this class. And we're going to see how it tells you all you need is potential, and you'll know everything you need to know about a material when it comes to mechanics. All right, thanks. I'll see you next time. Bye.